Here in this page right here, on page 188, we're seeing that balance being identified. And so we do have the back of the thyroid gland here. This is the thyroid gland positioned in the lower neck region, just behind the sternum. And the reason we're looking at the back side of it is because on the back there are these areas that are referred to as the parathyroid glands. They produce parathyroid hormone, PTH, and in the event that there's a falling blood calcium level, then PTH is released, and there's actually three things that it does. One is that it spares calcium at the kidney, so it doesn't end up in the urine. The second thing it does at the kidney is activate vitamin D in order to cause the uptake of calcium from food in the intestines. And the next thing that PTH does is that it's going to stimulate the activities of osteoclasts. Remember, the clasts here are types of macrophages that metabolize bone matrix. So we're going to break down some bone matrix and deliver calcium to the blood as a result of metabolizing the bone matrix. Now our bloodstream has more calcium. In some cases, maybe now we have more than enough. And so in that case, we can relax all of these features of PTH, and the blood calcium will calm down. Okay, so that's our situation. Here is a demonstration of Wolff's law that I wanted to show to you. If we were to cut through the bone here and reveal what the spicules look like in the spongy bone, you would see that the spicules are kind of lining up in the direction here of stress. And so basically what we're doing with this particular bone, because this is our femur, we're going from uniaxial at the spinal column to biaxial down both lower extremities. And we're changing the forces out here to the lateral aspect so that we can bear the weight of the body on two different sides. But you'll notice that there's all these other bone growths that are also due to Wolff's law. That is to say, when there is stress on the bone will respond and grow in relation to that stress to support the locomotive weight-bearing, as well as to support the stresses of the muscles that may be attached here. Okay, so that's part of the deal. And then let's see. They show us different types of fractures that occur. As I indicated to you before, it's about a 3-month period in which bones repair themselves fully. So bone matrix is actually remodeled over the course of about 100 days. And here we have an example. We have a little sequence here of a fracture. And of course, wherever there's a fracture, there's going to be blood flow. And here we actually see that the periosteum has been maintained, which is a somewhat rare situation. So that means we're limiting the blood loss right here. But nevertheless, there is a visible break in the bone. Then we have hyaline cartilage, or sometimes what we call spongy bone trabecula, invading through here. Okay, and there's going to be the nutrient vessels will become will proliferate so that they can take care of the nutrient necessities of this reprogramming situation. Here we have full-on trabecula completely formed through here. Okay, we still have some swelling, as you can see. Swelling is a feature of fractures that's going to go on for quite a while. And then finally we have the reformation of the matrix. Okay, so the bone repairs itself. This is a very fine feature because that means that I could actually, as an orthopedic surgeon, I could take a piece of bone from someplace in the body, maybe the iliac crest, and put it somewhere else, where it's possible bone loss has happened due to traumatic injury. Right? Somebody may have lost some part of their jaw or some part of their humerus, some aspect of other parts of the body were traumatically lost, and so we can actually take a piece of bone from one place and put it somewhere else. Okay, and it's fine to do that, this as long as the cells remain alive in the transfer situation. Okay, so then that brings us here to various issues of interest here, homeostatic imbalances. They talk about some of these things. You can check it out in your own personal reading with regard to Rickets Vitamin D, missing vitamin D due to too much indoor activity or being too far north in the latitudes in order to not get enough vitamin D exposure from the sun. We produce vitamin D as a response to sunlight. Osteoporosis is a situation in which the osteoclasts are breaking down bone to supply calcium to the blood, but we're not replacing the bone, either due to a problem in the diet or to a problem in the vigor of the tissue in terms of replacement. Okay, so there are all kinds of risk factors, menopause and aging in general being two significant risk factors. And so we have used hormone replacement therapy, especially estrogen, to women, but the side effects are often too great to proceed with that type of therapy. So they give us some bullets over here in terms of, let's see what they say. So there are several other factors that contribute to osteoporosis. One of them is petite body frame, so that there's not a great deal of weight bearing, small size, insufficient exercise to stress the bones or to actually create circulation and stimulate growth factor at night, a diet poor in calcium, protein, abnormal vitamin D receptors, or just not enough vitamin D, not enough exposure to sunlight. Smoking has a role to play. Hormone-related conditions might be encountered in some of that. Okay, so I'm not going to get into some of these more rare diseases, but I will show you a picture of this individual here. So here we have the fetal primary ossification centers at the time of 12 weeks. There are no bones in this individual. These are simply centers of ossification. And the density, the radiopacity that you see there is a result of cartilage and cellular structures that are present there. These are not necessarily actually bones themselves, right? But they're sort of bones as a suggestion, shall we say. You can see that the growth centers are not even present very much in the way of the wrist bones right there. Okay, so at least we have the outline of bones everywhere. Okay, so and then we'll conclude this chapter.